Exponential growth. To fully understand exponential growth, we're going to do a little first comparison between linear and exponential so you can kind of see the difference. So consider the following situation. A grassroots campaign decides to run a fundraiser that takes in $1 donations. The campaign initially receives 30 $1 donations. So that's our initial. The hope is to get 20 additional each week. So if they start with 30, week 1, they're going to get 20 more. We would hope to have 50, right? Because we had 30, we want to get 20 more. Week 2, we want to get 20 more. That would put us at 70, right? So they want to get just 20 more every week. It's a good theory. So if you think about that, if they start with 30 and then they get 50, well, let's write it so you can read it. Then they get 50, then they get 70, then they get 90, then they get 110, right? 20 each week. Well, let's find the absolute, relative, and percent increase. It's an increase because it's going up. So remember, absolute change is new minus old. Relative change, new minus old divided by old. Percent increase, just change the percent or the decimal to a percent by multiplying by 100%. Okay, so let's do one together, and then I'm going to ask you to hit pause and try the rest on your own. So if we take, this would be new, here's old. New minus old gives me an absolute change of 20. Then to find my new minus old, so then I would take that and divide by old, which is 30, and I would get 0.67. Change that to a percent, I would have 67%. Okay, actually I'll do one more before I ask you to go on your own. So now I would say, okay, now 70 is new, 50 is old. So 70 minus 50 gives me an absolute change of 20. I divide that by the old value, which is 50, gives me 0.4, and I have a 40% increase. Okay, I would like you to hit pause and try to do 90 and 110, then come back and check your answers. Okay, you can see for each one we have an absolute change of 20, which makes sense because we added 20 each time. And the relative change is different for each one because each time we're dividing by a different denominator. And when you divide, even though you have 20 in the numerator, if you're dividing by a different denominator, it's going to give you a different change, right? Different relative change. So how is the amount of donations changing? We added 20, right? What's staying the same? The absolute change. Staying the same. So if we think about this, how can we mathematically find the amount of donations in week 6? Well, we started with 30. We know we're doing 20 each week. So if I would take 20 times 6 and then add it to what I started with, that would give me how many I should have in week 6, right? Thinking about it. So we can then write a model. Use the initial value for week 0. Well, initial value, we call that a starting point. That would be our y-intercept. The absolute change, the reoccurring change, we call that slope. So I can write an equation, y equals slope times x plus my y-intercept, where x represents the number of weeks. This is a linear model. So if absolute is the same, you have a linear model, and your absolute change is your slope. Isn't that great, the way that works? So if you have absolute change, we have the y equals mx plus b, where the slope is the actual absolute change, and your y-intercept is still your starting point. That hasn't changed. Okay, let's try another strategy. The campaign fundraiser asked each donor to get 3 of their friends to donate $1. Then each of those donors gets 3 friends after that, and so on and so forth. So if each of the 30 donors found 3 friends, well, 30 donors, each found 3 friends, we would have 90 donations in the first week, right? Because you have 30 people, and each one of those is bringing 3. So 30 times 3 friends each gives me 90 total donors. So if we're talking about our chart, those 30 people found 3, and we had 90. Now we have 90 people. Each one of those 90 people finds 3. So 90 times 3 more, we're going to have 270 the following week. Then each of those 270 finds 3 more, and we have 810. And then each of those find 3 more, and we have 2430. Right? So each one is finding 3 more, and that's why it's growing so rapidly. So let's find our absolute. Remember, again, absolute change, new minus old divided by old, and multiply by 100%. Okay, so let's find our absolute change for the first one. So new, old. So 90 minus 30 gives me an absolute change of 60. I take that, I divide by old, and I get a relative change of 2, which is a 200% increase. And that's excellent. That's what we want. Let's go to the next week where we have new and old. So new minus old gives me 180. My absolute change is 180. I divide it by the old, which is 90, and it gives me 2. Multiply by 100, 200%. Okay, finish out 3 and 4. Hit pause. Try those. Come back. All right, pretty easy to see that the absolute change continues to get bigger because we have a bigger difference between values, while the relative change stays the same. Each time our relative change is 2, which gives us a 2% increase each year. How are the number of donations changing from week to week? Well, we multiplied by 3. They're tripling. They're tripling from year to week to week. Mathematical rule would be multiply by 3. Which value is staying the same? Clearly the relative change, it's 2 or 200% for each one. Besides continuing the table, how can you mathematically find the amount of donations in week 6? Well, we're repeatedly multiplying by 3. So I'm going to write that down. Repeatedly multiplying by 3. Repeated multiplication in the mathematics world is known as exponents. So how many times do you want to multiply by 3? And the answer is 6. 3 to the 6th power would give me how many I should have then, but don't forget, I had to start with 30. So if you would take 30 times 3 to the 6th power, that would give us how many donations we had in week 6. Because you had to start somewhere, right? 30 times 3 gave us the next one. Then we multiplied by 3 again, then by 3 again, then by 3 again. So the repeated multiplication means we need an exponent. So you can see that leads us into the exponential growth model. And so we're going to have the amount equals the initial amount, and sometimes I'm going to actually use correct notation here. The initial amount is like a sub 0. That means initial amount. Inside you have your growth factor raised to the time period. And there is your formula. Now there are 2 ways to find the growth factor. Here's one. 1 plus the percent increase. The 1 represents how much you started with. So think about it. If you started with 30 and you multiply by 1, you have 30. So that 1 just helps you keep the data that you have. Okay, so our percent increase in our example was 200%. Well, if we're going to play with that inside a math problem, I have to change it to a decimal, and 200% is just 2 as a decimal. So my growth factor in this particular problem would be a 3. And hopefully that makes sense because things triple, right? You multiplied by 3 in your table. So that makes my growth factor a 3. All right, so let's move on to the next page here. Another way to find the growth factor is to divide 2 consecutive data points. So on our last one, for week 4, we had 2430, and in week 3, we had 810. So this would be new, this is old. If I would use 2430 divided by 810, I get 3. So if you have data, you can always just divide new divided by old, and that will give you your growth factor. So in your formula, the 3 is what would go in, right? So we would say y equals 30, growth factor of 3 raised to the time period. Or you could use x if you wanted, and that would work for our problem. Now let's apply this. Suppose an investment earned 12% per year in compound interest. Annually, the growth factor would be 1 plus 12% would be 0.12, and it gives me 1.12. So how much would be in the account after 10 years if $1,000 was invested? Well, initial amount, growth factor, time. Right? This is how we would figure it out. Now, mathematically, you have to do the exponents first. So depending on your calculator, some of you can type it in exactly how you see it. Some are going to have to find the 1.12 raised to the 10th power, get an answer, then multiply by 1,000. But either way, you should get $3,105.85. And let's go to 16. According to the United Nations, in the year 2000, the world population was approximately 6.2 billion. Respond to the following, assuming the population has grown by 1% a year. Okay, let's find growth factor. while the growth factor is 1 plus the percent increase. So here's 1%, that's 0.01. So 1 plus 0.01, my growth factor is 1.01. What unit is time measured in? It says per year, so we're talking years. That makes it nice and easy. What is the exponential equation? Using the population for 2000 as a starting point, so again, that was 6.2 billion. So y equals initial amount, I'm just going to remember that it's in billions, growth factor raised to the time, and time is number of years. So let's estimate the world population for 2014. Now remember, we started with 2000. So for 2000, x is 0. So that means for 2014, x is 14. So in my model, y equals 6.2 times 1.01 to the x. I need to plug in 14 for x. So y equals 6.2 times 1.01 to the 14th power. I do the exponents first, then multiply by 6.2, and I'm going to round to 7.13 billion. And that would be the estimated world population. Again, it's an estimate. Using these models are estimates for 2014. And that, my friends, is the end of your intro to exponential growth.